Hello guys, welcome to this part of RC analysis. Now I will be discussing one of the important questions that is being asked in the interviews. So let's get started with the question. So given here is a first order RC circuit in which C1, C, R1 are in parallel and R2 and C2 are in parallel, in which the Vin is a step input of amplitude 5 volts and we have to find the output waveform across this branch. Okay, so here we have three conditions here. So the first one being R1 C1 greater than R2 C2, and second condition being R1 C1 lesser than R2 C2, and third condition being R1 C1 equal to R2 C2. So as usual we will find the output voltage at t is equal to 0 and at t is equal to infinite, and we will plot the output waveform. So at t is equal to 0, the equivalent circuit of the parallel combination of resistance and capacitance is simply a capacitance of the given value. So here the given value is C1 and C2, so I have replaced the circuit with C1 and C2 being in series combination. So as you guys know, this is a capacitance voltage divided circuit. The output voltage across the capacitance C2 is equal to V in C1 divided by C1 plus C2. Okay, we can simplify this equation as V in divided by 1 plus C2 by C1. Okay, this can be just derived by dividing the numerator and denominator by C1. Okay, now we have to find the value of output voltage at t is equal to infinite. At t is equal to infinite, the capacitances are open circuited. So we will just consider the resistances in series. Okay, this is just a voltage divider circuit, so the output voltage is given by R2 into V in divided by R1 plus R2. So if we can simplify this equation by dividing numerator and denominator by R2, we will get the output voltage as V in divided by 1 plus R1 by R2. Okay, now we will try to plot the output waveform. We are given with three conditions, so I will start with the first one. So here the first condition being R1 C1 greater than R2 C2. By replacing the C1 terms, we get R1 divided by R2 greater than C2 divided by C1, right? So we'll try to find the output at t is equal to 0 and infinite using this relation. Okay, as you can see here, R1 divided by R2 is much greater than C2 by C1. We can conclude that plus V divided by 1 plus R1 divided by R2 is this term is much lesser than this term. Okay, now we can conclude that this is smaller than this thing. So this is the value of output at t is equal to 0. So at t is equal to 0, the value is higher, and as time moves on, the value becomes smaller and smaller and reaches to a constant value. So I have assumed this thing to be the V out at t is equal to 0, and this value to be the value of V out at t is equal to infinite. So this thing decreases exponentially and reaches the constant value. So this is the output waveform. Now in order to find the time constant of this equation, we just look into this circuit and we find that the time constant of this equation turns out to be parallel combination of capacitances multiplied with parallel combination of resistances. So this is the corresponding time constant here. Similarly, for the second question, given R1 C1 is much lesser than R2 C2, which means R1 by R2 is much lesser than C2 by C1. So Vn divided by 1 plus R1 by R2 is greater than Vn divided by 1 plus C2 by C1, right? So this is at t is equal to 0 and this is at t is equal to infinite. So the value of v out at t is equal to infinite is greater than value of t is equal to value of v out at t is equal to 0, right? So this will be the corresponding plot for the output waveform. So for the third condition, where the R1 C1 is equal to R2 C2, both the values at t is equal to 0 and t is equal to infinite are equal. So this will be just a single line at the amplitude of Vn divided by 1 plus C2 by C1, or Vn divided by 1 plus R1 by R2, because both the values are same, right? So this is regarding the time domain analysis. Now the interviewers might also ask you to plot the frequency domain of this circuit. So in order to do that, first of all you need to know what is meant by Bode plot. So what is a Bode plot? It is a plot between the frequency and amplitude, in which the frequency is represented in logarithmic scale and the amplitude is represented in decibel scale. So if you see here, I have given you an example of high pass filter in which the frequencies are denoted in powers of 10. This is 10 to the power 0, 10 power 1, 10 power 2, and it goes on. And in case of magnitude, it is denoted in the dBs, minus 40 dB, minus 30 dB, until 10 dBs. Okay, as this is a high pass filter, the signal in the lower frequencies are attenuated, and in the signals in the higher frequencies are at 0 dB. Okay, so in order to find the Bode plot for a given circuit, one should know the response of the circuit at omega is equal to 0 and at omega is equal to infinite. One should also know the poles and zeros of the circuit. Okay, so first now we will try to find the response of the circuit at omega is equal to 0. So if you see here, the response of the circuit at omega is equal to 0. So as we all know that if here in this circuit the impedance of the capacitance is Zc is given by 1 by Cs. Okay, so S is here, this is given by omega j into omega. Okay, now at omega is equal to 0, the impedance of the capacitance is just infinite, so it is open circuit. So the circuit can be replaced with just the series combination of R1 and R2. So that is what I have done here, and the output turns out to be simple voltage divided circuit, which is R2 divided by R1 plus R2. And at omega is equal to infinite, the capacitance is short circuited, because this is given by Cs and S tends to infinite. So 1 by infinite, it is equal to 0. So it is short circuited, and if it's short circuited, then we have to consider the impedances of the capacitances. So if we consider the impedances of the capacitances, then it turns out to be a capacitance voltage divider circuit. So the Hs or H omega is given by C1 divided by C1 plus C2. So now that we have got the response of the circuit at omega is equal to 0 and omega is equal to infinite, we will try to find the poles and zeros of the circuit. In order to find the poles and zeros, there is a simple trick which I will be discussing in the upcoming video. So as of now, in order to find the pole, one should ground the input and try to find the effective capacitances and resistance across the given circuit. Okay, so that turns out to be C1 plus C2 multiplied with R1 parallel with R2. Okay, so if you have found out that, then the pole location is just the inverse of that C equivalent multiplied with R equivalent. Okay, and in order to find the zero of the circuit, this branch of the circuit must be infinite, or this part of the circuit must be 0. As you can see that this part of the circuit can't be 0, because if this thing turns to be 0, then this thing also turns to be 0, right? So that can't be possible, that is overruled. Okay, so we will try to find if this thing can turn to be infinite. So if in series parallel combination of capacitance and resistance, uh, if the equivalent should become infinite, then the impedances 1 by Cs must be equal to minus R1, right? So the S becomes minus 1 by R1 C1. So we'll neglect the minus sign, and this is the 0 of the circuit. Don't worry if you guys didn't understand how to find this. I'll be discussing this in detail in upcoming video. Okay. And one more thing in Bode plot is that whenever in the frequency response you approach a pole, the slope of the response decreases by 20 decibel per decade, and if you approach a 0, the slope of the response increases by 20 decibel per decade. Okay, keep this thing in the mind. Now we will plot the frequency domain analysis. Okay, so the first question being R1C1 greater than R2C2, R1C1 greater than R2C2, which is R1 by R2 greater than C2 by C1, right? This is at omega is equal to 0. So if you just rearrange the terms, this thing turns out to be 1 divided by 1 plus R1 by R2, and this thing turns out to be 1 divided by C2 by C1 plus 1, right? So if this is greater than this thing, then this thing will be smaller than the okay, let me write it down. 1 by 1 plus R1 divided by R2 will be smaller than 1 divided by 1 plus C2 by C1. So this is at omega is equal to 0, and this is at omega is equal to infinite. So the value at omega is equal to 0 is lesser than value at omega is equal to infinite. So we will get a plot something like this. And as I had said earlier, when you approach a 0, the plot will increase, the slope of the plot will increase by 20 decibel per decade, right? So this is 20 decibel per decade slope increment, and as you approach a pole, the plot will decrement by 20 decibel per decade slope. Okay, this is at this is when R1C1 is much greater than R2C2. In the similar way, you can also find the frequency plot at R1C1 much lesser than R2C2. This is just inversion of this plot, or you can say mirroring of this plot here. Okay, so and the third and final condition is when R1C1 is equal to R2C2, right? So as you can see, both these values are equal. This will be a single straight line at the value of 20 log 1 by 1 plus R1 plus C2. This will be the amplitude of this plot here. Okay, thank you for watching this video. I will meet you guys in